Hi, this is week 15 of AP Physics, and in this lesson we'll talk about the following topics. We'll be talking about gravitational potential energy at a distance. We're also going to go ahead and talk about inertia. We're also going to discuss the potential energy in a spring, and we're going to wrap it up with power and work and their relationship to each other. Alright, so for our lesson objectives, students will learn the effects of distance on gravitational potential energy. Students will also learn the effects of radius and mass on inertia. Finally, students will understand the relationship between power and work. So let's start with gravitational potential energy at a distance. Near the surface of the planet, this will be the formula that you would use, where it's mass times gravity times height. Now, what if you're further away from the planet? This formula no longer works. The reason why it doesn't work is because of the g. See, g is 9.8 near the surface of the planet, but as you get further and further and further away, that value is no longer 9.8, so therefore that messes with the formula. So what do you do if you have two objects that are far away from each other? This is the formula you will want to use. So at larger distances, the formula is modified to be this. Potential energy due to gravity is g multiplied times m1 times m2 over the r. G is a universal constant, so it is going to be 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. M1 and M2 is the mass of the two objects you're measuring. So for example, you might have a battle station and a planet. And R is the distance between them. Remember, that's from the center of your battle station to the center of the planet. Alright, so we're going to go ahead and use that formula to solve for problem number 23. In problem 23, they ask you the following question. A planet orbits a star along an elliptical path as shown in the figure. Consider the system consisting of the planet and the star. How do the magnitude of the force exerted on the planet by the star and the total mechanical energy of the system change as the planet moves from point X to point Y? So here's our diagram. So here's point X, and as our planet is moving towards point Y, what's happening to the gravitational potential energy and what is happening to the overall mechanical energy for the whole system. So let's go ahead and start with the first part, which is what happens to the potential energy due to gravity. We're giving these options A, B, C, D. Magnitude of the force exerted on the planet, does it increase or decrease? Well, if you look at the formula for potential energy at a distance, you're going to see the following. The radius. The radius is in the denominator, so therefore it is inversely proportional to the gravitational potential energy. So as the radius decreases, because the planet and the star are getting closer to each other, so as the radius decreases, the gravitational potential energy will increase. So we've narrowed down to either A or B. As far as the mechanical energy, in this system, the mechanical energy will be conserved. Whatever potential energy is lost, it is gained as kinetic energy because the planet increases as it approaches a star. So therefore, it will remain constant. So therefore, the answer for problem 29 is A. Up next for us, we're going to go ahead and take a look at moment of inertia and rotational kinetic energy. Moment of inertia is the inertia of a rotating body with respect to its rotation. It is a rotating body's resistance to angular acceleration or deceleration. So if you have an object that has a very large mass, that's going to have a lot of inertia. Also, if it has a very large radius, it's also going to have a lot of inertia as well. So if you have an object with a lot of inertia, it's going to be very difficult to take it from rest and get it moving. But once you get it moving, then it's going to be very difficult to go ahead and bring it back to rest. So the more inertia it has, the more resistance it has to change, either accelerating or decelerating the object, slowing it up or speeding it up. Alright, so inertia is not just mass and radius that affect it, it's also the shape. So let's go ahead and take a look at a couple of shapes. So if you have a solid sphere versus a hollow sphere, like a basketball, then the formula for inertia changes. For a solid sphere, inertia is 2/5 mass times r squared. But if it's a hollow sphere, like a basketball, it's going to be 2/3 mass times radius squared. If you have a cylinder that is hollow versus one that is solid, then the hollow cylinder is going to be mass times radius squared versus the solid sphere cylinder is going to be 1/2 mass times radius squared. Even if you rotate the same rod, but one's from the center and another one from the edge, that's going to give you a different value for inertia. So inertia depends a lot on the shape of where the mass is distributed, mass, radius, overall shape. All of that takes into account inertia. Alright, a rotating rigid body may be considered to be a system and may have both translational and rotational kinetic energy. Rotational kinetic energy is calculated by this formula right there. Alright, so let's talk about translational versus rotational kinetic energy. Translational kinetic energy is the kinetic energy we think about when we think of an object in motion. So a car moving has kinetic energy. The actual term for it is translational because it's moving from one place to another. So that's translational kinetic energy. On the other hand, what if an object standing still in one spot but it's spinning? For example, you have your washer and the drum inside of it spinning. Does that have kinetic energy? It's not going anywhere. It does have kinetic energy. It is called rotational kinetic energy. Here's the formula, what is 1/2 I, and the I is inertia multiplied times the angular velocity squared. Now, quick reminder, whereas radius times angular velocity will give you velocity. So that's a quick relationship between angular velocity and velocity. You just got to multiply angular velocity times the radius. And we're going to use this formula to solve for example 7. Up next for us is example 7. In this problem they ask you as the following. A ball of mass m and radius r starts from rest at a height of 2 meters above the ground and rolls down a 30-degree slope. What is the linear speed of the ball when it leaves the incline? First of all, one of the things I want to address is the slope. The slope is going to be irrelevant to this problem. It does not matter. What does matter is how high it is off of the ground. It is 2 meters off of the ground, and that's really going to come into play, not the slope. Alright, so what we're going to go ahead and use to solve this formula is the conservation of mechanical energy. So mechanical energy initial is equal to mechanical energy final. Now, how do you get mechanical energy? Mechanical energy is all the kinetic energy plus all the potential energy. Here we got two types of kinetic energy. Translational kinetic energy as the ball moves down the ramp, and it also has rotational kinetic energy. So there's two types. So let's go ahead and write all of those down. Kinetic energy rotational initial plus kinetic energy translational initial is equal to plus gravitational potential energy initial is equal to rotational kinetic energy final plus translational kinetic energy final plus potential energy due to gravity final. Alright, so those are all our values. Now we're not going to use all of them. There's 3 of them that are actually going to get canceled out from the very beginning. The initial rotational and translational kinetic energy are not there. There's no value for them. And the reason why not is because the instant you let go of the ball, is the ball rotating yet? And this is no. So it's got no angular velocity. So that's why it's got no rotational kinetic energy initial. Is the ball already moving down the ramp the instant you let go of it? No. So it's got no initial kinetic energy because it's got no velocity. Now on the other side, it's this one that's going to go away. The potential energy due to gravity. Once the ball reaches the ground, it's got no height. No height means that one's gone. So these are the values that are left. Now we know that they're left. We're going to go ahead and use these formulas, plug them in, substitute. So let's go ahead and begin. It is mass times gravity times height initial. And that's equal to, on this side, rotational kinetic energy, which is 1/2 inertia times angular velocity squared plus 1/2 mass times velocity final square, and this is also final angular velocity. Alright, so now we're going to go ahead and keep on going. Our goal is to get that VF all by itself. We're going to isolate it. So we're going to work to do that. I'm going to get rid of the half first. I'm going to multiply both sides by 2. That's going to get rid of the halves, just simplifying things a little bit. So it's going to be 2mghi. It's equal to I times angular velocity final squared plus mass times velocity final squared. Next, you see this I for inertia. We're going to go ahead and substitute. They told us that we're going to assume it's a solid ball, and so it's going to be 2/5 mass times radius squared. Alright, so I'm going to substitute that for the I right here. So I'm going to rewrite everything except you're going to see that substitution for the I for this formula. So it's going to, the left side looks the same, and on the right side that I, it's really 2/5 mr squared, angular velocity squared, plus mass times velocity final squared. Next, our next substitution is going to take place right here. You see that r squared times angular velocity squared. If we go ahead and go back a slide, you see this formula. Radius times angular velocity equals velocity. We're going to go ahead and substitute this with a velocity. since both the radius is squared and the angular velocity is squared, we're going to end up with velocity squared as well. So now it'll look like this. Here's our formula now. Left side still the same, 2/5 mass. Now I'm going to put velocity final squared, because again, angular velocity times radius was velocity. So I substituted that. And mass times velocity final squared. Alright, let's keep on simplifying. You'll notice mass on all of them, so we can go ahead and divide it all by m, so it goes away. So now we're left with 2ghi is equal to 2/5 mass, nope, mass is gone, velocity final squared plus velocity final squared. Alright, so now we're going to go ahead and add them together, collect like terms. So this is 1 plus 2/5, so that's going to go ahead and give us 7/5. So it's going to be 2 times hi equals 7/5 velocity final squared after I added them together. Alright, now I want to go ahead and isolate that VF, so I want to get rid of the 7/5. So I'm going to multiply by 5/7 on both sides. So that way, see, they'll cancel each other out, since it's the inverse. And on this side, we're going to get 5/7. These guys cancel out, so we get velocity final squared. Finally isolated. On this side, 2 times 5/7, so it's going to give us 10/7 g times hi. Last step, I want the velocity final on its own. I want to get rid of the square, so I square root on both sides, giving me velocity final, and it is square root of 10/7 g times hi, and that is your formula. That's what we're going to use to figure out the velocity as the ball is rolling off of the ramp. Again, what about the 30 degrees? Irrelevant. The slope does not really matter. So unless you went down 2 meters, that will be your formula. Alright, so velocity final is going to be 7/10 multiplied times gravity, 10 meters per second. And the height was 2 meters. Square root that whole answer, and we will get our final answer. So that's going to go ahead and be 10 times 10 times 2 is 200 divided by 7. Square root of that answer will give us 5.35. And that is the answer for part A of example 7. Now in part B, they ask us the same question, but they're going to change the object. It says repeat this example, but for a solid cylinder. Now the inertia of a solid cylinder is here 1/2 mass times velocity, mass times radius squared. So that'll be it. So they want us to repeat the whole problem again, but this time with the cylinder. So let's go ahead and do that. Now I'm not going to go ahead and erase everything. Actually, this is where the change occurs in the I, the inertia. So I'm going to erase everything below that. And that's where we'll pick it up. Now I'm going to substitute this formula for inertia right here. So the left side will again look the same. And the inertia, it is 1/2 mass times radius squared, and then the angular velocity final squared plus mass times velocity final squared. Again, what are we going to do with this radius and angular velocity? Well, you guys know that the radius plus angular velocity, it will give you the velocity. So we're going to substitute that for velocity one more time. So this will be a formula now. 2 times mgh is equal to 1/2 mass, and that's going to be velocity final squared plus mass times velocity final squared. Alright, so now we can go ahead and combine like terms over here. So we're going to end up with this, 2 mass times gravity height initial. It's going to be 3/2 mass times velocity final squared. Alright, again, we're trying to isolate the velocity final, so we're going to go ahead and get rid of the m, divide by m on both sides. So it's going to be 3/2 velocity final, so the m is gone. Alright, I want to isolate the m, so I want to get rid of the 3/2, so I'm going to multiply by 2/3 on both sides. 2/3. So that will cancel that one out. Just give me velocity final. And on this side, it's going to be 4/3 g times h. Alright, I'm going to square root to get rid of the square. and that will give us our final velocity. It's going to be square root of 3 over 4 GHI. Alright, so now this was part A. For part B, let's plug in the values and solve for the final velocity if we had a cylinder instead of a ball. So it's going to be 4 over 3 multiplied times acceleration due to gravity times the height of 2 meters. And get the square root of that. And that's going to give us the following answer. So it's going to be 20 times 4 divided by 3, square root of that. So the answer for this problem, part B, it is 5.16 meters per second squared. Alright, so there you have it, part A and part B. We get different velocities because they have different inertias. So we get different values. Alright, that takes care of example 7, part A and B. Next, let's take a look at problem number 24. They ask you to rank from fastest to slowest when rolling down a ramp without slipping. Is it A, a solid ball, B, a hollow cylinder, or C, a solid cylinder? Alright, so for those, who's going to roll the fastest, who's going to roll the slowest? Well, that depends on their inertia. So we should take a look at the formula for inertia for each one of these. For the solid ball, it is 2/5 mass times radius squared. For a hollow cylinder, it is 1 mass times radius squared. And for the solid cylinder, it's 1/2 mass times radius squared. Alright, so those are the formulas. I'm going to change these fractions into decimals. Alright, so 2 over 5 is really 0.4. 1.0, let's just put it, 1.0. And 0.5 is going to be just a 0.5. So those are just their values. And now you can go ahead and easily compare them. So who's going to be the fastest out of all of these ones? Well, the fastest is going to be the one who gives you the least amount of resistance. Alright, so since they all have the same mass and radius, then this one with a 0.4, that's going to give you the least amount of resistance. That's going to go the fastest. So we'll label this one as fastest. Because it's got the smallest value, 0.4, 1, and 0.5. So therefore, who's going to be the slowest? This will be the slowest. Alright, so as far as ranking them from fastest to slowest, I would put A would be fastest, it would have the greater velocity, then who will be next? It will be C, and then finally B would be the slowest. So as far as velocity, A will be greater than C, and C will be greater than B. And that takes care of problem number 24. So we've had a discussion on potential energy because of gravity at a distance and near the surface of the Earth. But there's other types of potential energy. For example, potential energy held in a spring that has been compressed. So that's what we're going to go ahead and talk about that. Potential energy of a spring. So the force of a spring is conservative. So it's not lost. It is conserved. And its potential energy is given by this formula. Potential energy with an S right here, that's for a spring, is 1/2 K times X squared, where K is a constant for the spring, and X is how much the spring's being compressed, measured in meters. Now, the spring potential energy can be put into the work energy theorem. So, for non-conservative, you can have the change in kinetic energy plus the change in gravitational potential energy plus the change in potential energy in the spring, and that will give you the work for non-conservative. Now, if it is conservative, then you could set up the formula as such, where you have kinetic energy final, potential energy due to gravity final, and potential energy of a spring final is equal to kinetic energy initial, and gravitational potential initial, and potential energy of a spring initial as well on the other side, since they're equal to each other. So we're going to go ahead and use both of those formulas to go ahead and solve for example 8. Example 8 gives you the following. It says, a block with a mass of 5 kilograms attached to a horizontal spring with a spring constant of 400 newtons per meter. So there's the setup, as you can see in the picture. The surface of the block rests upon a frictionless surface, and if the block is pulled out 0.0500 meters and released, find the speed of the block when it first reaches the equilibrium point. The equilibrium point is when the spring is no longer either compressed nor stretched. So part B, find the speed when the compression is 0.025 meters, and C, repeat part A if friction acts on the block and the coefficient of friction is 0.15. Alright, so let's go ahead and get to part A for this problem. So find the speed of the block. on it. So we're going to go back and get some data out of the problem. First of all, we're going to need to know the mass of our object. So our block has a mass of 5 kilograms. Next, the constant, it is 400 newtons per meters for the spring. It's frictionless, and it is pulled to a total of, so here's our x, 0.0500 meters. Alright, so now we need to find at the equilibrium point the speed of the block. Alright, so we're going to go ahead and use the conservation of energy theorem. Since there's friction, we're not losing any energy. So we're going to go ahead and use this one right here, where you have the kinetic energy final. Well, we're going to put initial on the left. We've been doing that so far, so we're going to stick with the kinetic energy initial plus gravitational initial plus potential energy due to a spring initial, and that equals kinetic energy final plus gravitational final plus potential energy of a spring final. Alright, so now we've got all of those. Some of them we can go ahead and get rid of. For example, gravitational. Notice that the block is sitting on a surface, so it's not moving up or down, so there's no potential energy due to gravity taking place. So we're going to go ahead and get rid of those two. So let's simplify the formula a little bit. Alright, what else can we simplify? Well, initially, the instant we let go of the block, it's at rest. The block is at rest. So therefore, how much kinetic energy does it have initially? The answer is it has none. No kinetic energy initially. It does have a kinetic energy final. Finally, for the spring is compressed, so it does have potential energy of a spring initially, but once it reaches the equilibrium point, the spring is no longer compressed. So therefore, it's got no potential energy at that point. So now we cancel those out. We're left with these two. Let's go ahead and put in the formula. Alright, so for the potential energy of a spring, it is 1/2 K, the constant, times the compression squared, which is equal to kinetic energy 1/2 mass times velocity final squared. And again, you're looking for the speed. So in part A, find the speed of the block, so we'll be looking for velocity final. Alright, so we're going to go ahead and isolate it. First thing I'm going to go ahead and do is I'm going to get rid of the halves. I'm going to multiply both sides by 2. So I'm going to go ahead and do that. That's going to go ahead and give me kx squared equals mf final. Alright, and now we're going to go ahead and isolate the VF, so I'm going to divide by m on both sides. And that gives us this formula. And last step, I'm going to go ahead and square both sides, and that's going to go ahead and just give me VF, which is square root of k times x squared over m. So that will be our formula to solve for the velocity of the block once it reaches its equilibrium point. Alright, so let's go ahead and now plug in the values. So velocity final is going to be the constant, which is 400 newtons per meter, multiplied times the compression of the spring, which is 0.0500 meters squared, and that's going to go ahead and be divided by the m. The m is the mass, which is 5 kilograms, and that we're going to go ahead and square it. Alright, so we plug all of those into the calculator, and we get our answer for part A of this problem, which is going to go ahead and be 400 times 0.05 squared times, pardon me, divided by 5 kilograms. We get 0.2, and now we're going to go ahead and square root that, and the answer is going to be traveling at 0.447 meters per second. And that takes care of part A of example 8. In part B of example 8, they ask us to find the speed once again, but this time when the object is 0.050 meters. Okay, so now it started off as 0.05, now it's halfway to the equilibrium point. So we're going to go ahead and solve for that. So here we go, we have our conservation of mechanical energy one more time. Since it's frictionless, we're not losing any forces, and we're going to go ahead and get rid of some of these again. Potential energy due to gravity, immediately cross it out because that block's staying on the ground, so we can go ahead and cross it out. Now, kinetic energy initial, again, at the very instant you let go of that block, it's at rest, so therefore it's got no velocity, so we can go ahead and get rid of that. Last time we crossed out this one, potential energy of the spring, because the block was at the equilibrium point, so the spring was not compressed. But now we will have to keep it because although the spring has decompressed a little bit, it's still, there's some compression there, 0.025 meters of compression. So it is not completely decompressed, we're going to go ahead and keep it. Alright, so now let's go ahead and put the formulas for each one of these. So potential energy of a spring, initial is going to be 1/2 constant times the initial compression squared, which is equal to initial compression 0.05, equal to kinetic energy 1/2 mass times velocity final square, and that's what we're solving for. And over here we're going to put plus 1/2 K times the compression final squared. Alright, compression final is going to be 0.025. Now, we are solving for velocity final, so I'm going to collect like terms and move this one over. But before I do that, let's get rid of all the halves. So I'm going to multiply both sides by 2. So just to simplify the problem slightly, and that way we get rid of the halves. Here we go. Now I'm going to go ahead and move the constant times the compression final over to this side, and notice that that's an addition, so I'm going to have to subtract, so it's going to end up looking like this. Alright, and that's going to equal to the mass over the velocity final squared. Alright, so move that one over here. What's next for us? We could probably factor out the K, but instead I'm going to move the M over on this side and then factor out the K. Alright, so I'm going to go ahead and do that. Let's see, K xi squared minus xf squared over m, that equals to velocity final square. Alright, so that's going to go ahead and be our formula. Now, we're going to go ahead and square root both sides so we can just have the velocity final by itself. So I'm going to go ahead and erase this and put a square root symbol right there. So the square root of that, that's going to give us our velocity final squared. Then from there on, we just got to plug in our values and we'll get our answer. So we're going to say velocity final is equal to the constant, which is 400 newtons per meter, multiplied times initial compression of 0.0500 meters, and that is squared, minus 0.0250 meters, and that is also squared, and all of it divided by the mass of the block, which is still 5 kilograms, and we're going to square root it. So we're going to go ahead and get our calculator, go ahead and figure that out. Let's start with the subtraction, which we got to do the exponents first. So I'm going to do 0.0500 squared minus 0.0250 squared, and that's going to go ahead and give us 1.8 times 10 to the 1.875 times 10 to the negative 3. So that's what we get here. Multiply times 400. 0.75 divided by 5. 0.15, and now we're going to go ahead and square root it. It's going to give us an answer of 0.387. That is our velocity. 0.387 meters per second. And that is our velocity for part B of example 8. Up next for us is part C of example 8. In part C they ask, repeat part A. If friction acts on the block and the coefficient of friction is 0.15. Alright, so now we got to go ahead and redo part A. Quick reminder for part A, initially the spring was compressed, 0.05. At the end it was decompressed because we were at equilibrium. The constant for the spring was 400 newtons per meters. The mass of the block was 5 kilograms. And they're giving us now that we have friction of 0.15. Alright, since friction is a non-conservative, that means that it's going to get lost, the energy is going to get dissipated. We're going to go ahead and use this formula for work non-conservative because the energy is being dissipated, which is equal to the change in kinetic energy plus the change in potential energy due to gravity plus the change in potential energy for a spring. So we're going to go ahead and use that formula. Now, what is the amount of work that was done by the friction? Alright, let's go ahead and take a look at that. So I'm also going to need this formula, where it's work net, it's equal to force net times the distance that the block has traveled. By the way, the distance that the block has traveled is going to be the same as how much the spring was compressed. So those two values are the same. There you go. So now let's go ahead and continue. Now in this problem, let's see what was the force net. The force net will be, well, this one, force of the spring, since the spring is at equilibrium, it's not stretched, it's not compressed, that is a 0. Force gravity and force normal cancel each other out, so the only real force is going to be the force due to friction. So that's your only force remaining. So my force net is force due to friction. So I'm going to go ahead and substitute that there. Force net is equal to force friction times the distance. Alright, now what else do we know about force friction? Well, force friction is the coefficient times the normal force. So let's go ahead and put that there. Coefficient times normal force, that's force friction, times d, that's going to be your work net. Next, what do we know about the normal force? We know that the normal force is the same in magnitude as the gravitational force, which is mass times gravity. And we know what the mass is, and gravity is 10.0. So work net is equal to the constant times, let's see, it's going to be mass times gravity times d. Alright, so that's our work net. So that's the work done by the friction, which is going to go right there. So I'm going to go ahead and substitute that right there. I'm going to erase this because I'm going to need all the board space I can get. So it's going to be the coefficient times mass times gravity times the distance. That's going to give us this part. Alright, now let's look at the right hand side. What else can we get rid of? Well, this block's not going up or down, so there's no potential energy due to gravity here. There's no change, so that's a 0. Alright, so at least we summarize that a little bit. Next, in this formula, changing kinetic energy. Kinetic energy, changing kinetic energy is final minus initial, plus for the spring, it's going to be, again, final minus initial. Alright, but the final one for the spring is 0. Why? Because at the end, when it's at an equilibrium point, the final compression is 0. So that's going to get rid of the, oops, pardon me, I erased the wrong one. The final compression, it's got no final compression. Alright, so therefore, no potential energy for the spring final. Same thing for kinetic energy initial. As soon as the instant you let go of the block, it is not moving, it's got no velocity, so therefore kinetic energy initial also gone. So we can go ahead and summarize the formula a little bit more that way. It's going to go ahead and be N times G times D is equal to 1/2 mass times velocity squared final plus, in this case, 1/2 constant times compression initial squared. Alright, so that is our formula. Let's go ahead and keep on working to isolate the VF because I want to know what is the final velocity. Alright, so we're going to go ahead and do that. And let's see. When I isolate it, first I want to get rid of all the halves. I want to multiply everything by 2. So 2, it's equal to 2 constant times mass times gravity times the distance is being compressed, mass velocity final squared plus constant compression initial squared. I want the VF by itself. I want to get rid of this. You see that positive, so I'm going to go ahead and subtract, move it over on this side. Okay, ooh, pardon me, no, that's not a positive. You see that negative right there? That means this is negative. And that is negative as well. There we go. Alright, so now I'm going to go ahead and move it over on this side. Since it's a negative, I'm going to add this to both sides, so I'm going to end up with this. Plus Ki squared equals mVF squared. There we go. Alright, what's next for me? I want to isolate the VF again, so we're going to get rid of the mass. So I'm going to divide by mass on both sides, so we're going to end up with this. It's equal to mass over here, velocity final right there. And then lastly, I'm going to go ahead and square root it to get rid of that square. And that's going to go ahead and give us our formula for this problem. Alright, now, there's a little something that should be here. Friction. Friction is working against the movement of the block. If the block's moving out, then friction is going to be working against it. Okay, so Therefore, friction is going to be negative. So where's our friction? Here we go. Remember, work friction, here we go. So this is actually, I'm going to throw in a negative right there because it's going against our movement. Alright, so keep that in mind. That's a negative. Alright, now we got everything there. We can go ahead and plug in all the numbers that we got and come up with the answer. So let's go ahead and do that. So it's going to be velocity final is equal to 2 times the constant 0.15 times mass, which is 5 kilograms, times the distance, gravity, times the distance it was stretched, 0.05 meters, plus the constant, which is 400, multiplied times the compression initial, 0.05 squared, and all of it divided by the mass, which is 5 kilograms. Don't forget I said that was negative right there, because friction is working against us, so we're going to go ahead and lose energy because of friction. Alright, I'm going to go ahead and do these two parts separate, so I'm going to start with 2 times 0.15 times 5 times 10 times 0.05. It's going to give me 0.75 negative on this side, plus, let's see, 0.05 squared times 400. It's going to give me 1, and all of this is going to be square rooted, and that's going to be our velocity final. Alright, so let's plug it into the calculator. The answer comes out to be 0.223 meters per second. So yeah, we lost some velocity because there is friction, and again the friction was working against us, which is why we ended up giving that negative value there. Alright, that takes care of part C of example 8. Next for us is problem 25. The problem asks the following. It says, in the case of friction, what percent of the mechanical energy was lost by the time the mass first reached the equilibrium point? So we're going to go ahead and compare mechanical energy final versus mechanical energy initial. So the whatever's missing, that is what went to friction, and then we'll get the percentage of that from the initial value. Alright, so at the end, let's see, mechanical energy final is kinetic energy final plus potential energy of spring final. At the end, the spring was not compressed nor stretched out, it was at equilibrium, so therefore there's no value for this one. It only had kinetic energy, and that is 1/2 mass times velocity final square. Plugging in the value is going to be 1/2 the mass, which was 5 kilograms, and for part C our velocity was 0.223 meters per second squared. So the final mechanical energy for the system was 0.223 squared times 0.5 times 5 equals 0.124. Alright, so that is our final mechanical energy in joules. Our initial mechanical energy was, let's see, kinetic energy. No, we didn't have it. Initially that block was not in motion, but the spring was compressed, so we do have a initial potential energy of a spring. So that is 1/2 the constant times the compression initial squared. So that will be 1/2 the constant, which is 400 newtons per meter, multiplied times the compression, which is 0.0500 meters squared. So the initial amount of mechanical energy was 0.05 squared times 400 divided by 2, 0.500 joules. Alright, so what percent is this from that? This is what remained. That's what we got. So what remained? That's what we started with. Let's see, it's going to be 0.124 joules over 0.005. This is how much energy was left over. So it's going to be 0.124 divided by 0.5 times 100, because we want a percent. So that gives us 24.8%. But that's what was left over, right? The question was, how much was lost? So if 24% remained, then the answer would be 100 minus 24.8. 75.2% was lost, which is what they asked for. Because that's what was left over. So therefore, that's how much was lost. That takes care of problem number 25. Up next for us, let's go ahead and take a look at problem 26. In this one, they tell you, suppose the spring in the last sample starts at x equals 0 and the attached object is given a kick to the right so that its initial speed is 0.6 meters per second. What distance from the origin does the object travel before coming to rest, assuming that the surface is frictionless? That's important to note. So we have our spring. At first it was completely decompressed, attached to the object. Someone kicks it and it goes out. As it goes out with this initial velocity of 0.6. Eventually the spring is going to go ahead and come to rest. Since it's attached to the spring, it's going to stretch, but eventually will come to rest. So final velocity, I'm going to squeeze it here. Well, let me put it at the bottom. Final velocity therefore is going to be 0 meters per second. And they're saying how far will it go before it stops? That's what they want to know. So they want to know what is x, which is a compression, or how much the spring stretch, in this case, final. Alright, so it is frictionless, so therefore we're going to assume that all the energy is conserved. So let's see, it's going to be mechanical energy initial is equal to mechanical energy final because there's no friction, so we're conserving all our energy. Alright, what is mechanical energy? Is kinetic plus potential put together. So we're going to put kinetic initial plus potential energy of a spring initial, it's equal to kinetic final plus potential energy of the spring final. Alright, so that is our setup. We can go ahead and get rid of some stuff. For example, since we know that at the end the velocity is going to be 0, therefore it's got no kinetic energy at the end. And at the beginning, the spring was not compressed. Initial compression of spring is 0, it's not compressed, so therefore it's got no potential energy of the spring, so that's gone. Simplifying our formula a little bit. Alright, so now let's go ahead and start plugging in values. So we're going to have for this formula, kinetic energy initial, 1/2 mass times velocity initial, and that's going to be squared. And on the other side, it's going to go ahead and be 1/2 the constant times the compression final squared. And compression final, that's what we're looking for in this problem. So we want to go ahead and isolate it. So we're going to get rid of the halves. We're going to move the k over here. Let's get started. I'm going to multiply both sides by 2, giving me m times vi squared equals kxf squared. Now we're going to move the k over on this side by division. So we're going to go ahead and divide. Gives us this. And finally, how do I get rid of the square? I square root on both sides. Square root here and a square root on this side. That gives us the square goes away. Alright, so that is our formula for solving how much did this spring stretch out before it came to rest. Alright, so it's going to be the mass, 5 kilograms, multiplied times the initial velocity, which was 0.6 meters per second squared, and that's going to be divided by the constant, which is 400 meters per newton, and then we square root it, and that gives us the final. In this case, it's not compression, but instead how much the spring was stretched out. Alright, so let's put it 0.6 squared times 5 divided by 400, and then square root of that answer. It's going to be stretched by 0.067 meters. That is how much the spring was stretched. That takes care of problem number 26. In problem 27, we ask the following question. Which of the following equations correctly indicates the total mechanical energy of the system in figure 3? So total mechanical energy. Remember, mechanical energy's got potential and kinetic energy. So kinetic energy, is there here any? And the answer is no. There's no kinetic energy because the ball stops. So there's no kinetic energy. So now we're down to potential energy due to gravity and potential energy of a spring. The spring is compressed, so it does have potential energy of a spring. If we take a look at the options that they give us, notice that they all have the same potential energy due to the spring. So what's really a question is the potential energy due to gravity. Which one is it? It's not B because it does have potential energy due to gravity. It is not on the floor. This is potential kinetic energy, so it's not A, not B. So we're down to either C or D. Should we add the potential energy due to gravity or subtract it? Alright, well the answer, let's take a look at the problem again. this spring is not compressed, so that's a 0. So this one is below the 0, so therefore that's a negative for the compression. Therefore the answer will be here with the negative, letter D. That's your answer for this problem. In problem 28, we're asked, at which point does the block have the greatest amount of kinetic energy? Remember, kinetic energy increases as the velocity increases. So what you're really looking for is, when is the block moving the fastest? Okay, so when here the block is compressed, so the spring is compressed, and so therefore it's not moving very fast. Here, when it reaches equilibrium point, and I can tell because the friction and the spring are equal to each other, that's when the spring's moving the fastest. So therefore your answer, that will be your answer. That's the one who has the greatest amount of kinetic energy. Here, now the spring's being stretched out, it is slowing down the block. So if it's slowing down the block, it's losing velocity. So it's neither X or Z. The answer is Y. And you can see here the friction and the spring is at the equilibrium point. So therefore it has the highest amount of velocity. So therefore it has the highest amount of kinetic energy. Next is problem 29. In this problem they ask you, a block on a horizontal surface is placed in contact with a light spring with a spring constant of K, as shown in figure 1, which we'll see in a bit. When the block is moved to the left so that the spring is compressed a distance of D from its equilibrium length, the potential energy of the stored in the spring block system is EM. When the second block of double the mass is placed on the same surface and the spring is compressed a distance of 2D, as shown in figure 2, how much potential energy is stored in the spring compared to its original potential energy of EM? Then say all frictional forces are considered to be negligible. And here's the diagrams that we're talking about. So they're going to go ahead and compress it. This one distance of D, and this one twice as much. They're going to compress it from the equilibrium point. And they also double the mass. So now they're saying, how will that affect the potential energy of the spring? And there's the key, the potential energy of the spring. They're not talking about the block. So the fact that this block is twice as much is completely irrelevant to this problem. So initially they said this, we have a constant of K, and we compress it by D. We're going to put it here as just X squared, and that gives us M. So what happens if we double the compression? Alright, so this is what it will look like for the second problem. It will be, let's double that compression squared. So what would that give us? It would give us, that's going to go ahead and be 2 squared, that would be a 4. We'll put 4x squared. So I'm going to move it around slightly. Remember that is EM, so that will be 4 times as much. So the answer for this problem will be letter D. The next section we're going to go ahead and discuss is power and work. Now let's get the definition for work. Energy can be transferred by an external force exerted on an object that moves the object through a distance. This energy transfer is called work. So when you get an object that has mass and you go ahead and put a force on it and move it through a distance, that is work. You got to put force over a distance. Here's the formula for it, and that'll give us work. That also is the change in mechanical energy. Now what about power? Power is defined as the rate of energy transferred into or out of or within a system. So power is equal to the change in mechanical energy, which is also work, divided over time. So if I go ahead and push that object over a distance, but it takes me a lot of time, therefore I use less power. But if I were to get that object and put force on it over the same distance, but I do it much quicker, so in less time, that's going to require more power. For the formula, we can go ahead and change it slightly. So its power is equal to the change in mechanical energy over time, which is also can be changed into work over time, and work is force times distance over time, and distance over time, well, that's what we refer to as velocity. So force times distance can also go ahead and be used to get power. Now what is the unit that we use to calculate power? That is the watt. So the unit of power is the joule per second, which is also called a watt, named after James Watt. That would also be written as kilograms times meters squared over seconds cubed. Up next, we're going to go ahead and take a look at example 9 and use this formula to go ahead and solve that problem. In example 9, we're asked the following question. It says a 1,000 kilogram elevator carries a maximum load of 800 kilograms. A constant frictional force of 4,000 newtons slows the motion upward. what minimum power in kilowatts that the motor must deliver to lift the fully loaded elevator cart at a constant speed of 3 meters per second. Alright, so let's go ahead and take a look at a free body diagram of all the forces acting on this elevator. There's of course force of gravity pushing down on it. There's also a frictional force on this elevator of 4,000 newtons, and of course there's force tension. Okay, so force tension is the one we're concerned with as far as figuring out how much power the motor is delivering, because the motor is pulling this elevator upwards at 3 meters per second constantly. So what we're going to go ahead and do is figure out what is this force tension. We know what the force of friction is. That is a total of 4,000 newtons. And for the force of gravity, it's mass times gravity. So we know that it's 10,000 for just the elevator and 800 for the load. That will be the people inside the elevator. So total mass for the elevator fully loaded will be 1,800 kilograms. Multiply the mass 1,800 kilograms times gravity, which you're going to use 10 meters per second squared. That's going to go ahead and give us a force of 18,000 newtons. Alright, so if we got friction going down and gravity also pointing down, how much is force tension? Well, force tension, since we're moving at a constant velocity, it must be the same in magnitude. So that's going to be 22,000 newtons. Alright, so that will give us our force tension. Now, to go ahead and figure out the power, that's going to go ahead and power is equal to force times the velocity. Okay, so the force tension will go here in that case, so it's going to be 22,000. And the velocity of this elevator is 3 meters per second. So we go ahead and we multiply 22,000 times 3, and that's going to go ahead and give us 66,000 watts. Alright. Now, they did ask for the answer in kilowatts, so we're going to go ahead and divide it by 1,000. So our answer will be 66 kilowatts, and that is the power being delivered by the motor as it's pulling the elevator up at a constant 3 meters per second. Alright, let's go ahead and take a look at the next problem. The next problem is problem 30. And this one say, in general, are the minimum power requirements for the elevator cart ascending, going up, at a constant velocity greater than, less than, or equal to the minimum power requirement of an elevator descending, going down at a constant velocity? Well, ascending, the elevator is fighting gravity, so it's got to overcome gravity, so therefore it needs to do more work. But going downward, the elevator is assisted by gravity, so it's got to do less work. So therefore the answer for this one, it says going up, it will be greater. Alright, let's go ahead and take a look at our next problem, and this is going to be our last problem for this lesson. Problem 31. Suppose the same elevator cart with the same load descends at 3 meters per second. So now it's going down at 3 meters per second. What is the minimum power requirement? And here the motor removes the energy from the elevator cart by not allowing the elevator cart to free fall. Alright, so now we are going down, same velocity, 3 meters per second, in the downwards direction. So I'm going to go ahead and change this to a negative. Okay, and in this scenario, our friction now, it's going to be slowing the elevator down. So our friction is going to be pointing in the other direction. Okay, so we're going to go ahead and put it here in this direction. Force of friction, it's going to go ahead and be 4,000 newtons. Okay, so now, if that's 18,000, that's 4,000. So what is the force tension? Force tension from the cable, it's going to go ahead and be 18,000 minus 4,000 because they got to match in magnitude, the top and the bottom. So it's going to go ahead and be 14,000 newtons. That's a force tension. Alright, so that is our new value. Next, we're going to go ahead and figure out how much power is required. So for the power, it's going to go ahead and be 14,000 newtons, and I'm moving at a velocity of 3 meters per second. Alright, so we go ahead and multiply both of these. So 14,000 times 3 goes ahead and gives us 42,000 watts. And again, they likely want the answer in kilowatts again, so it's going to be 42 kilowatts just divided by 1,000 to get the answer. And that goes ahead and takes care of problem number 31. This also brings us to the end of week 15 for AP Physics, and thank you so much for watching the video.